Hi everyone, my name is Chen, and I'll be presenting our paper, What is HDR? Perceptual Impact of Luminance and Contrast in Immersive Displays, on behalf of my colleagues at NYU and Meta. So first, HDR stands for High Dynamic Range. And what do people think of when they typically hear HDR? So this can mean file formats that can store a wider range of contrast and luminance than what is typical, or hardware and algorithms that can capture real scenes more faithfully, or display systems that can reproduce a wider contrast and luminance range than a traditional display. This third category is what we're interested in exploring in this project. So how do we know when a display can be considered HDR? We want to answer this question by studying the most important properties of a display, its contrast and peak luminance. Our hope is that we can determine some mapping between these two variables to their impact on the display's image quality, but before I describe how we collected this data, I'll go over some background. So, for example, when you go to the store to buy a commercial display, you may find that there's this VESA Display HDR sticker on it, and this just certifies the display you're buying is considered HDR. And this list defines an industry standard for tiers of HDR displays based on factors like its peak luminance, its contrast ratio, and more. However, the peak luminance and contrast at the lower end of this list are pretty common for displays these days. For instance, my MacBook Pro can reproduce 1,000 nits of peak luminance and 1,000,000 to 1 contrast. And while this is the industry standard, we weren't able to find a perceptual rationale for how it was created. A few papers have studied this idea in terms of human preference. For example, a paper by Daly and others studied user preference for different exposure parameters in diffuse scenes, as well as different peak luminances for scenes with specular highlights. And their study data, however, is very limited to cinema conditions, and so much so that they even simulated exit sign lighting during their study. This work by Matsuda, Chapiro, and others was conducted in a prototype HDR VR display. And they asked users to adjust the exposure of pass-through VR scenes, and they found that users preferred a higher mean luminance for indoor compared to outdoor scenes. Researchers have also studied the simultaneous dynamic range of the human visual system. Kukul and Reinhard conducted this study where users were shown a brief flash of a stimulus placed on an adaptation background. They found that the visual system has a simultaneous dynamic range of greater than 3.7 log nits, and they suggest that a good display should approximate that range. So to summarize, the daily work modified max luminance and kind of studied contrast in their highlight study, but their study focused heavily on cinema. The work from Matsuda and Shapiro also studied max luminance, and the contrast of their content was varied, and the study was conducted in a VR setting. However, they focused very heavily on pass-through VR content. Our work is the first that studies both contrast and peak luminance in an immersive VR scenario. And let's say we have a hypothetical result. So we tested a bunch of displays with different contrast and peak luminances, and we now have their quality, where quality increases here with brighter cell color. At the bottom left, we could test parameters for a commercial VR headset, which might have limitations due to its form factor and its optics. And at the top right, we have a prototype display, which can reach very high peak luminance and reproduce a wide range of contrast. So with this type of data, we can make design decisions. For example, we can answer the question of whether we should make the next generation display brighter or should we have higher contrast. And I'll describe how we collect this data in the rest of the talk. So our study was like this. We conducted a two-interval forced choice experiment where users were asked to choose one of two test videos that look closer to the reference HDR video. And these stimuli were shown on an HDR haploscope display, and each HDR display consisted of an ISO CG3146 professional HDR reference monitor. And these displays can reach 1,000 nits peak luminance and 1,000,000 to 1 contrast and can reproduce an HDR color gamut. The setup was very carefully calibrated by a mechanical engineer such that the system field of view is 65.7 degrees, and the mirrors steer the light path to the user's eyes and can reflect more than 98% of visible light. And one thing that we had to consider was the crossing of the display's light paths, which could reduce the contrast significantly, which we show here on the inset photograph. And we resolved this by building an enclosure around the two displays. We studied 5 different contrasts and 5 different peak luminance conditions with logarithmic steps in each direction up to the limits of our HDR testbed. And these display conditions were simulated using tone mapping. So we chose a very simple S-shaped curve, and we simulated decreases in peak luminance by rolling off the highlight and contrast change by adding black level. We also studied two different tone mapping schemes, one fixed tone mapper independent of the scene content, and another that adjusts the amount of highlight reduction based on the scene. Here we show that the content-aware version can preserve more details in bright regions like the woman's dress than the fixed tone mapper. We also very carefully selected our video content with the goal of capturing a dataset that's representative of VR use cases. So this includes things like productivity, faces, user-generated content, and entertainment content. In total, we studied 12 scenes, 5 different contrast and 5 different peak luminance conditions, and we used 2 tone mappers to simulate those. We ran the study on 41 participants in total. We used an active sampling algorithm called ASAP that adaptively selects stimuli to show users, and this allows us to significantly reduce the length of study sessions. We further reduced the size of the study by showing users 4 of the 12 scenes in a session, and this let us fit the study into a single hour with 153 trials in total. The results of the user study were scaled to this perceptual just objectionable difference, or JOD scale, and we show those results here. So what we can see is that as contrast and peak luminance increase, quality generally increases as well. But we also notice that as contrast increases, the perceptual quality saturates at some point. And we fit a polynomial model to this data for both tone mappers, shown as a 3D surface here with the 2D slices shown on the right. And the model maps black level and peak luminance to perceptual impact. So one thing is that our stimuli was shown on an HDR haploscope, which may not be super representative of typical VR scenarios that include optical elements that might reduce contrast. And we wanted to test whether our model works for this type of VR scenario. So we use this HDR VR display from Matsuda, Chapiro, and others. And this display can produce up to 21,000 nits peak luminance and 400,000 to 1 contrast. And in this headset, we conducted a rating-based study where we showed users 360 degrees HDR scenes mapped to different peak luminances. And users were asked to rate the map test scene with respect to the reference on this 5-point quality scale. We found that the study ratings on the x-axis correlated really well with our model predictions on the y-axis. So we can say that our model kind of generalizes to this VR scenario. And now we can apply the model for really cool applications like display quality prediction. Here on the x-axis is contrast, and on the y-axis is peak luminance. And the yellower colors here represent parameters that result in higher quality. And here we show the product baseline and compare to the prototype limit with parameters of our HDR display. And now we can use our model to calculate the quality of the VESA display HDR tier list. So contour lines here represent parameters that yield equal quality, and the scatter points are the parameters representing each tier in the tier list. And we can also plot additional displays here, given we know their peak luminance and contrast. So for example, a home projector, a laptop, a standard office monitor, and an HDR television. So here we chose displays with parameters that span the range of this quality scale. We can also use this model for display design. So for example, let's focus in on these 2 points on the quality ISO line. We can design power efficient displays using our model, and prior work has found that the display component consume up to 40% of an entire VR device's power consumption. As a result, if we reduce the luminance or if we dim the display, we can reduce the display's power consumption. So let's assume a hypothetical display can produce 400 nits of peak luminance. If we dim the display by 25% to 300 nits, this would save 25% on display power. However, if we want to maintain image quality as predicted by this ISO line, we would have to increase the display's contrast from 1300 to 1 to 5580 to 1. And these sorts of considerations could be interesting to a VR display manufacturer that needs to consider the cost-benefit trade-offs of power versus hardware that can boost contrast. Thank you so much for listening, and please come to our poster if you have any questions.